So in this first video, we're going to formally define what artificial intelligence is, and we're also going to distinguish it from some common related words that people often tend to intermix and even interchange, even though they do have slightly different definitions. And hopefully some of this will feel like a review because we did talk about this in our initial Intro to Computing lecture for engineers. And just to reiterate what I said there, I really think that over the next 10 years, the one skill that people will assume that engineers have as it relates to computing is the ability to understand and build AI models. So the first kind of set of words that people tend to intermix is artificial intelligence, or AI, and machine learning. So here are just kind of some distinguishing definitions between the two. But the simpler way that I think about it is when you're talking about AI, you're talking about the general kind of problem of trying to make computers act like humans. Not in any particular way. You just think about robots, right? You want computing machines to behave in a human-like fashion. Versus machine learning is a very, very specific way of doing that. It is particularly trying to get computers to behave like humans by showing it a bunch of data and trying to have it infer underlying patterns of data. So if you look at the actual definition that they've given here for machine learning, how can we make machines improve through experience? Particularly what we're talking about there is showing it examples of what we'll see more formally later on is referred to as training data, and then hoping by exposing it to that training data that it can kind of replicate those patterns or generalize them on some testing data. So just think of ML as a subset of AI. AI, the general problem of trying to make computers like machines. ML, the particular task of trying to make computers like machines through showing them prior examples which come in the form of data. So you can kind of see that relationship here in that Venn diagram. Notice that machine learning is a subset of artificial intelligence, meaning that anything that's machine learning is AI, but anything that's AI isn't machine learning. Within that, you see an even deeper, smaller subset, I should say, of both artificial intelligence along with machine learning, and that is the idea of deep learning. And as we'll see a little bit later on, that is referring to a particular type of machine learning where the models consist of these artificial neural networks that generally have a lot of layers to them. And that term will make sense a little bit in a minute. But if you think of machine learning as trying to teach computers to learn patterns in data, deep learning is doing that with a particular subset or type of model. Another term that you hear a lot is this idea of data science. And you notice that data science kind of intersects artificial intelligence and all of its subfields in this Venn diagram. But there's also a subfield of data science that kind of sits out there independently. And the easiest way to think about this intersection at the subset at least, is whether you're working with machine learning, where you're particularly trying to get machines to learn patterns in data, or you're working with more general artificial intelligence. Generally speaking, in order to make a machine act like a human, you're going to need to show it some examples. Whether or not it's trying to replicate the pattern in those examples or not is really irrelevant. Just know that the field of data science, which generally speaking refers to all the mechanisms of how you design pathways to gather data, to clean data. You hear a lot of terms like data pipelining. That's just a fancy way to say how do you go from the point of actually gathering the data to taking it in through some information technology workflow and getting it to a place that you can work with easy. Data cleaning refers to the fact that, particularly as engineers, if we build hardware systems to capture data, very often that won't be perfect data, and we'll need to do some cleaning before we actually place it into any type of numerical algorithm like some AI algorithm. So when you think about how machine learning works, typically it follows this workflow here. Remember that what you're trying to do is to get a computer to learn patterns through data. So the first thing that you have to do is collect the raw data. As we mentioned in step 2, generally that data is not going to be perfect. You're going to have to do some cleaning to it. That is data preparation. So you can kind of think of steps 1 and 2 as the data science subsets of machine learning. Then 3, you're going to select a model. I'm sure all of you have fit a bunch of data to a line before. Believe it or not, that linear regression process is actually an example of machine learning. It's just in that case, you're working with a particular model, a line, and you're trying to learn the best relationship of the parameters, the slope and the y-intercept, to best fit the data that you have. Once you've picked which model you're going to try to learn the parameters for, the training process is basically iteratively tuning in a general process those parameters to make the model fit the training data. Validation, improving the model, is just kind of an iterative step of trying to get a better model, usually given a subset of data that you call your validation set. So for those of you that have heard the basics of machine learning, you've probably heard about taking a data set and splitting it into a portion for training, a portion for validation, and a portion for actual testing on. So we won't kind of in this course get into the difference between validation And the training set, just think about really what's going on in the training set, is the set of parameters in the model that are learnable are being iteratively tuned. And validation, you're usually using to tune what are known as hyperparameters. And you'll see an example of that when we talk about artificial neural networks. And then finally, what is it all useful for if you don't actually use your model to make predictions at the end? So when you think about machine learning, one thing that you want to know is that there are three subsets of it: supervised learning, unsupervised learning, and reinforcement learning. And when you think about what supervised learning is, what you're trying to do is, given a set of data that actually has labels, to learn a relationship between the output and the input. So you can think about, if I gave you a bunch of images of cats and dogs, and for each of those images, and remember, an image is going to be nothing more than a collection of data. At each pixel, you're going to have, assuming that they're colored images, particular red, green, and blue values at the pixel level. If I also gave you labels for each image, if I said this label is a cat and this label is a dog, what the machine learning algorithm would be trying to do in that case for supervised learning is to be able to take an unknown image and either label it as a cat or a dog. So it's trying to learn a particular relationship between inputs, in this case images, and outputs, in this case a binary label of is it a cat or is it a dog. Unsupervised learning would be that same kind of task, but imagine that the images didn't actually have labels to them. So the underlying data set is still a bunch of cats and dogs, but you don't know which one is which. In unsupervised learning, you might be trying to get a model to basically cluster and find similarities in the underlying data without telling it, hey, that's a cat, that's a dog, learn how to label a cat and dog. You're just saying, hey, here's a bunch of data, see if you can find any patterns in it. And given that kind of assumptions of the underlying data set, it would probably be able to cluster them into two groups. At least that would be the hope. So usually you use unsupervised learning when you just got a bunch of kind of unstructured data and you don't necessarily know the underlying relationships of it, and you're just trying to put it into groups. Reinforcement learning, a relatively new field in machine learning, which is really useful in tasks like robotics and autonomous driving. What you're trying to do is get an algorithm to get very good at making sequential decisions. So if you think about how the autonomous driving looks, you have all the sensors on your car. Maybe it's a LiDAR sensor, an acoustic sensor, maybe it's a video. And at every time step, you're having to decide whether to accelerate or brake and whether to turn your wheel. So in reinforcement learning, that's basically what you're doing. You're iteratively making a set of decisions to try to optimize some long-term objective. In the case of a car, it's of course to get to your end destination without crashing. So a quick question, which of these problems is forecasting sound most similar to? I'll be honest with you, I took this set of notes from another class where I was using these slides, and they are working at the problem of forecasting, which is given a time series trying to predict some future value. That is a case of supervised learning, because in that case, what you're trying to do, the actual input data that you're working with are prior samples of the time series, and the labels are future values of the time series that you know. So in the case of the weather, you can imagine if I gave you 365 days of the temperature in San Antonio, and you broke it down or you windowed it into a bunch of 7-day windows, and you tried to predict the 8th day, that's an example of time series forecasting. And in that case, that day that's right outside the window would be the label that you're trying to learn. So supervised learning, we've kind of talked about this. I've used the term labels beforehand, so I won't repeat that again. But this is the MNIST data set. It's a common set of images that you see in the initial stages of a machine learning course, or particularly a computer vision course. And this data set was made popular when the post office was trying to design solutions to automatically read handwritten addresses off of envelopes. And for us, it's very easy to say, hey, this is a 5 and that is a 5. But if you were trying to design a computer algorithm and actually give parameters to tell the difference, maybe you would say, oh, the way you look for a 5 is you look for a vertical line on the top, and then you look for a horizontal line beneath it, and then you look for something that looks like a C. So that works. Some 5s look like that, but not everyone writes a 5 like that. So if you were to design a set of rules to tell what a 5 is, any rule-based algorithm that you design is going to be fragile. It's going to break for certain cases. But think about it. Even a kid that's just learning their number systems, they can look at this and they can look at this. And even though they look different, they can probably say in both cases, hey, that's a 5. So that is what supervised learning is trying to do. In this case, the labels are the actual what are known as the ground truth digits of each number within that data set. and the input data is the actual images. So hopefully that made sense. The main thing that I'm going to look for you to do in the discussion board assignment that I'm going to give you is to just, in your own words, tell the difference between artificial intelligence and machine learning. Just know that machine learning is a subset of AI. AI in general is trying to get machines to think like humans. Machine learning is trying to get machines to think like humans by learning patterns and data. In addition, I might ask you something about the three different types of actual supervised learning, or sorry, machine learning in that case. So supervised learning, unsupervised learning, and reinforcement learning. So I will see you all in the next video.